Let's look at this first chapter of A2 Physics syllabus, Motion in a Circle. The first subtopic here, radians. You look at the first point here, radian. 1 radian is the angle subtended at the center of the circle by an arc of length equal to the radius of the circle. In order to understand the meaning of 1 radian, let us look at the diagram here. You can see the arc length is the curve over here, and let's say the arc length is 3 cm, and this is the radius of the circle. And if let's say the radius is 3 cm as well, this is where the arc length is equal to the radius. In that case, the angle subtended here is going to be 1 radian. So 1 radian is true whenever the arc length is equal to the radius. If you have 10 cm for the arc length and 10 cm for the radius, the angle here is also 1 radian. And just for your information also, 1 radian is about 57 degrees and 18 minutes. So let's move on to the second point, angular displacement. So angular displacement is the angle through which an object moves through a circle. So the formula given here, S equal to R theta. I believe that you learned this formula in maths, and we have to know that the S here is the arc length, the R here is the radius, and the theta here is the angle in radian. So what is angular displacement? You can see it mentions that it is the angle. It is the angle. So which means our angular displacement is actually the theta over here. So let me label down. The angular displacement is actually the theta. It's the theta. It's the theta, and which means we have this theta as angular displacement. And how about the S here? So what I said just now, S is actually the arc length. Arc length. Or you can also call it linear displacement. And R is the radius. From here, we have to know that the angular displacement is, for example, if a particle is moving in a circular track, the angle it makes is called the angular displacement. And because of that, angular displacement is just the angle. And from here, we need to know that the angle, the units for theta should be in radian. So let's move on with the second subtopic here. 1.2, angular velocity. So we look at the first point here. They said angular velocity, the rate of change of the angular positions of an object as it moves along a curved path. So the idea here is the rate of change of the angular positions. Okay, so let's start from the basic concept of displacement and velocity. So if you have displacement, let's say S as the displacement, and we know that if you divide by time, then you will get velocity. So this is the basic concept of displacement. Displacement divided by time is velocity. So the unit of displacement, the SI unit is meter, and the SI unit for velocity is just meter per second. So this is the basic concept for displacement and velocity. So over here, we normally call this linear displacement, and this is called linear velocity. So how about our situation here? Angular displacement and angular velocity. So in fact, it applies the same concept. Angular displacement, which is theta, and if you take this theta, you divide by time, then you will get angular velocity. So the symbol for angular velocity is omega. Okay, it's omega. And let's look at the unit at the same time. Like what I said just now, the unit for angular displacement is radian. And when you divide by time, you get angular velocity. So logically, the unit for angular velocity should be radian per second. So let's look at the formula here. As you can see, the formula is written as omega equal to theta over time. So based on the explanation here, it should be reasonable. So where theta is the angular displacement, the unit is radian, so the t here is the time. Angular displacement divided by time is equal to angular velocity. So angular velocity, the symbol is called omega, and the unit is radian per second. So the meaning of angular velocity basically is how much angle it makes in a particular time. So that is angular velocity. Now let's look at the next point, period. The time taken by the body to complete the circular path once. So when you see they said complete the circular path once, that means the particle make a complete circle, and the time taken for the particle to move for a complete circle is called a period. So let's look at the basic formula again. Our angular velocity is omega equal to theta over time. So we can extend our concept over here, where we replace the theta with 2 pi. 2 pi is 360 degrees, so which means the particle move one complete round, and the corresponding time for moving a complete round is called a period, and that's why the t at the bottom here is replaced by capital T, which is a period. So beside that, you can see another form here. The second form that is given here is 2 pi f, and f stands for frequency. So we can take the second formula in this way. We know that frequency is 1 over period. So when you have omega equal to 2 pi over t, and you factorize the 2 pi, you get 2 pi multiplied with 1 over t, and hence the 1 over t is replaced by frequency. So that's how we get the second formula. So let's look at the third point here, relating angular velocity and linear velocity. So remember, angular velocity here is the omega. Linear velocity here is the v. So the formula to relate these two is actually v equal to omega multiplied with r. So we need to know how we get this formula. So let's look at the working here. I start from the basic concept, which is here, displacement divided by time equal to velocity. So let me write down, velocity equal to displacement over time. And based on the formula here, s equal to r theta, I substitute it to the numerator. So I get r theta on top and t at the bottom, and I factorize the r. Theta over t is omega. So that is how we get v equal to r omega. So altogether, we have learned one formula. I put it in the blue box, s equal to r theta. Second formula, omega equal to theta over t. Third formula, omega equal to 2 pi over capital T, or 2 pi frequency. And third formula, v equal to omega multiplied with r. So altogether, there are 4 formulas. Now let us apply our concept in these questions. The drum of a spin dryer has a radius of 20 cm and rotates at 600 revolutions per minute. Show that the angular velocity is 63 radian per second. So in order to show the answer, let's look at our information here. 600 revolutions per minute. So you have to know that one revolution is one round. To make one round, the angle involved is 2 pi. So I write down the information. 1 revolutions the angle is 2 pi. So here we have 600 revolutions. So the angle will be 600 times 2 pi. Okay, so this is the angular displacement. So the angular displacement for 600 revolution is 600 times 2 pi. And our formula for angular velocity is omega equal to theta over t. So the theta here, the angular displacement is 600 times 2 pi, as that makes 600 revolutions. So let us write down 600 times 2 pi at the numerator. And the time involved is 1 minute, as you can see here, per minute. That means in 1 minute, the drum spins by 600 times 2 pi. So this is 1 minute, and the SI unit for 1 minute is 60 seconds. So 1 times 60. And by doing so, you can just check with calculator. 600 times 2 pi divide by 60. So you will get 62.8. 62.8, which is round up to 63 radian per second. Now let's look at B. Calculate for a point on the edge of the drum its linear velocity. So in order to find out the linear velocity, we can use formula V equal to R omega. So the R here is the radius, and the radius is 20 cm. So 20 cm in SI unit is 0.2 meter. Multiply with the angular velocity, which is 62.8, and hence you will get 12.6. And don't forget that for linear velocity, the unit is meter per second. So let us see more examples on page 8. So we look at page 8 straight away. Let us look at the question here. A cyclist is traveling at a speed of 13 meter per second. So when you see the unit meter per second, you need to know that this is linear velocity and not angular velocity. As angular velocity, the unit is radian per second. So let me write down, this is V. It is not omega. Okay. Now let us move on. 13 meter per second on a bicycle which has wheels of radius 390 millimeter. Calculate the time for one rotation of the wheel. Okay, so what we need to count here is the time for one rotation of the wheel. So we have to know the relationship between the linear velocity and the angular velocity. In order to understand the relation, let us start with the drawing of the view of the bicycle. So this is the view, and this is the ground. This is the center of the circle. And the wheel has a radius of 390 millimeter. Okay, so let's say this is the radius, R, and we know that R equal to 390 millimeter. In terms of SI unit, it should be 390 multiplied with 10 to the power of minus 3 meter. So this is the radius in meter. And as the wheel rolls forward, there is a relationship between the circumference and the distance traveled. So let's say I count out the circumference of the circle. Circumference is equal to 2 pi r, and hence I have 2 pi multiplied with 390 times 10 to the power of minus 3. And by calculating this, or let's say I just leave it like this first, I don't want to count the circumference, I just leave it in this form. So let's see the relationship between the circumference and the distance traveled. So imagine that you see blue color here. Imagine that the bicycle wheel turn one complete round. Okay, so when it moves one complete round, the bicycle will at the same time move forward by one circumference. So let's say I call this one circumference, then as well. So that is the relationship between the circumference and the distance traveled. Okay, so they are having a direct relationship. So which means when the wheel move by one circumference, then the bicycle move forward by one circumference as well. Okay, so that is the relationship between the circumference and the distance traveled. Now, what we are going to do here is we are looking for, you see the question again, we are looking for the time for one rotation of the wheel. So one rotation of the wheel, that is one circumference. One circumference, one round, okay, one round. So that is 2 pi multiplied with 390 times 10 to the power of minus 3. So this is at the same time the distance traveled by the bicycle. So we have the distance traveled. Okay, so let me write down first. This is also equal to the distance traveled by the bicycle. So we have distance now. We also have the speed. So as you can see here, this is the speed. So you have distance, you have speed, and you want to find time. So we can make use of the formula. Speed equal to distance over time. By rearranging this formula, you will get time equal to distance over speed. The distance is 2 pi multiplied with 390 times 10 to the power of minus 3, and the speed is given in the question, which is here. It is 13 meters per second. So by calculating this, you will get 0.188 seconds. So this is the time. Okay, the time for one rotation of the wheel. Now let's look at the part B of the questions, B1. The frequency of rotations of the wheel. So in order to find the frequency of rotations, so we need to know that what we have now, the 0.188 here, is actually the period. Okay, is the period. And we have to know that frequency is equal to 1 over period. So you have 1 over 0.188, and of course you have to keep the full decimal of these answers in your calculator, and you just press 1 over answer. That means you do 1 over the periods in with full decimals, and because of that you will get an accurate answer of 5.31 hertz. Now let's look at part 2 then. Part 2, the question said the number of rotations of the wheels in 1 minute. In order to answer this part, so we have to know the meaning of the frequency here. So the frequency here is 5.31. So it means the rotation is 5.31 rotations in 1 second. And our question asks for the number of rotation in 1 minute. So we have to multiply by 60 in order to get 1 minute here. So you have 5.31 multiplied with 60 as well for the rotations in 1 minute. Now 5.31 times 60, you will get 318 rotations in 1 minute. So that's the answer for B part 2. So let us look at the next questions. A cyclist traveled at the speeds of 12 meters per second on a bicycle which has views of radius 0.40 meter. So again, we are given with V, we are given with R. So A, the frequency of rotation of each view. So in order to find the frequency, basically we can use back the same concept as in question 1, where first I can count the circumference, and this time I'm going to write it down straight away. I'm going to write the distance traveled by the bicycle is equal to the circumference of the view, so which is 2 pi r. So I will get 2.51 meter. So this is the circumference, one complete round, and the distance is 2.51. And we make use of the same concept like question 1 just now. Speed equal to distance over time, and hence time equal to distance over speed. So the time here is a period. Okay, it's a period, as what we considered here is 1 round. So the time for 1 round is a period. So the distance traveled is 1 round, which is 2.51. The speed is 12. And by pressing calculator, you will get, if you keep all the decimals in your calculator, you get 1/15 pi. Or in decimal, this is 0.209. So you get a period here. So this is period. This is, let's say this is capital T. So frequency is 1/period, and hence you will get 4.77 hertz, or exact form 15/pi hertz. So this is the answer for part A. For part B, the angular velocity of each view. One of the way to do this is by thinking of V equal to R omega. As we know V, which is 12, and radius is 0.40, so omega is what we are going to find. So from here, by rearranging this, we will get 12 divided by 0.40, and we will get 30 radian per second. You may also use omega equal to theta over t as the formula to find the angular velocity, where theta, let's say, is 2 pi. So that is 1 round, and we know that when it is 2 pi, then the time span will be the time for 1 complete oscillations. So that is period. We already know the period is 1/15 pi. You can substitute 1/15 pi at the bottom here, and you cut the pi, you get 30 radian per second. So these are the ways to do it. And let's look at part C. The angle the view turns through in 0.10 second in radians, and part 2 in degree. So in order to do these questions, so what we need to do is we consider omega equal to theta over t, and hence theta equal to omega multiplied with t. So omega we already know is 30 and the time is 0.1. So from here we will get theta as 3 radian. This is C part 1. And for C part 2, we have to change 3 radians to degree. So we take 3 multiply with 180 over pi. We get 171.9 degree. Let us continue with 1.3 now. 1.3 circular motion. A body moving in a circle at a constant speed changes velocity since its direction changes. Thus, it is accelerating and hence experiences a force. So to understand this statement, let's take a look at the drawing here. We have a circle, and the particles on the circle move with the same speed. Let's say the speed is v meter per second. So when it's here, it has the speed of v meter per second. When it's staying at this point, it has a speed of v meter per second, and so on. So it has the same speed everywhere on the circular track. But the thing is, when we consider velocity, velocity is a vector quantity. Vector quantity has magnitude and direction. The magnitude of the particles is the same, which is v meter per second. But as you can see, the directions is not same. When it's here, the direction is to the right. When it's here, the direction is downwards. And when it is here, the direction is like this. So since it has different directions, the velocity is not a constant velocity, although the speed is constant. So it has a constant magnitude but different direction, and hence the velocity changes. Because of this, the acceleration is also non-zero. As what we know here is acceleration is equal to 0 when the velocity is constant. So the velocity here is not a constant, and hence acceleration should have value. And at the meantime, when you look at our Newton's second law, F equal to ma, when you have value for acceleration, then you should have value for F. Okay, so that's why the statement here mentioned that the particle should experience a force. Okay, so we have a force because of that. And what kind of force is that? You can look at the second point. It is called the centripetal force. So what is centripetal force? You can see here. It is the resultant force acting on an object moving in a circle, always directed towards the center of the circle. So to understand centripetal force, maybe I can put it in this way. It is actually the force that is necessary to keep an object moving in a circular path. So centripetal force is the force to keep an object moving in a circular path. And centripetal force is directed towards the center of rotation. So from here, what can I say is, if an object has centripetal force, then the object will continue to move in a circular track. If an object does not have centripetal force, then the object will not move in a circular track. That is the first part. And the second part that we are going to care about is, they also mentioned that centripetal force is the resultant force. So in order to understand resultant force, let's see one example here. If you have a particle moving in a vertical circular track, this is the particle. The particle has weight equal to mg, and let's say there is a string which hang the particle. So because of that, there is a tension of the string that act upwards. So according to the statement over here, they mentioned that it is the resultant force. Centripetal force is the resultant force that acts towards the center of the circle. So in order to find out the resultant force that acts towards the center of the circle, so I have to assume that the tension is the positive directions, okay, positive direction, and the weight is the negative direction. So to find the centripetal force, I can put it in this way. Centripetal force at this particular point, you can use tension minus mg. So that is the resultant force. If let's say the particle continue its circular motions and reach somewhere above of the circle, so you can look at the blue color, the particle reach here. In this situation, the tension is acting downward, the weight of the particle is also acting downward. So because of that, the centripetal force must be the resultant force that acts towards the center of the circle, and we assume the downward is positive in this case. So because of that, there are two forces that acts downward, which is tensions and the weight mg. So hence from here you can see that centripetal force, which is the resultant force, and hence it is equal to tension plus mg. So the second example that I can give here is, if you have a ceiling like this and you have a string that hang the particles, and the particle is moving in a horizontal circular track. So in these situations, we have tensions that act in this way, and let's say there is an angle of theta from the vertical, as you can see in the diagram. Now in order to find the centripetal force, so what we can do is we have to resolve the tensions. We have to resolve the tensions by finding the horizontal components, as this is the force that acts towards the center of circle. So in order to find this, so we can just use, as this is opposite of the angle, so we can use sine. This is t sine theta then. If you are wondering whether we should consider the weight over here, as you can see, weight acts downwards, which is 90 degree from the blue color force here. So it contributes no value to the centripetal force. So because of that, the centripetal force is equal to T sine theta for this case. So let's move on. The formula for centripetal force, as you can see here, F equal to mv squared over r. This is the first option. And the second option is mr omega square. So if linear velocity is given, you may consider the first formula. If angular velocity is given, you may consider the second formula. Now let's look at the next one, centripetal accelerations. So as you know, F equal to ma. If there is a centripetal force, which is the force that acts towards the center of the circle, if there is such force, of course, there should have a corresponding acceleration. So this is called centripetal acceleration. So remember that centripetal acceleration, same like centripetal force, its direction is acting towards the center of circle as well. So that is centripetal acceleration. Okay, so let us put it in this way. If you look at this circle again, centripetal acceleration is the acceleration that acts towards the center of circle. You can see it in blue color. So this blue color arrow which point towards the center of circle, this is centripetal acceleration. And how about the accelerations that acts in this particular way, this way, let's say, which is same direction with the linear velocity. So of course this is called linear acceleration. So the acceleration in this direction is linear acceleration, and the acceleration in this direction is called the centripetal acceleration. So in order to understand centripetal acceleration, it is kind of easy if you start from Newton's second law, F equal to ma. So centripetal acceleration is the one without m. Okay, it's the one without m. So as you can see here, if I have F equal to ma, so which my F is mv squared over r. So I cut the m, so I know that a is equal to v squared over r. So likewise, if I have F equal to ma again, where my F is mr omega square, I cut the m on both sides, then you will know that a equal to r omega square. So you can see it over here, our two formula, where you get it by simplifying the Newton's second law, cut the m on both sides, and you will get these two forms. So now we have two sets of formula. So the first one is the centripetal force, and the second one is the centripetal accelerations. So let's look at the next page. So we have a past year question here. Number 1, define the radian. Okay, so as you can see in the notes, page 1, so radians, I already explained it. And now here, let's look at the answer straight away. So radian is actually angle subtended at the center of circle. This is one point. Second point, by an arc equal in length to the radius of the circle. So the important words here is the arc is equal to the radius. Okay, so in that case, you will get 1 radian. Now let's look at part 2. A small mass is attached to a string. The mass is rotating about a fixed point P. So fixed point P is basically the center of the circle at constant speed as shown in figure 1.1. So you can see it, constant speed for the particles. Explain what is meant by the angular speed about point P of the mass. So you know angular speed. So angular speed, basically you should think of angle divided by time. So we can put it in this way then. Angle swept out per unit time. Or you can also say rate of change of angle by the string. Okay, now let's look at part B. A horizontal flat plate is free to rotate about a vertical axis through its center as shown in figure 1.2. So you can see it here. This is a horizontal flat plate which is rotating. A small mass M is placed on the plate. This is the mass. A distance d from the axis of rotation. So you can see distance d here. So basically the distance d is the radius. The speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. The maximum frictional force F between the plate and the mass is given by the expressions F equal to 0.72 W, where W is the weight of the mass M. The distance D is 35 cm. Determine the maximum number of revolutions of the plates per minute for the mass M to remain on the plate. Explain your working. Okay, so in order to answer these questions, first we need to know about the centripetal force. Okay, centripetal force. So recall back the note where it mentioned that centripetal force is the resultant force that acts toward the center of the circle. As you can see in this situation, the small mass M which stay over here, it is at the point of slide off the plate. So the motion is basically outward as it's going to slide off. So if the motion is acting outward, that means the friction which is opposing the motion, so the friction should act inward. Okay, so I call it FF, which is frictions. So the friction should act inward. And this is the only force that acts towards the center of circle. And because of that, this frictional force provides or contributes to centripetal force. Okay, so that is the first thing that we are going to mention. As you can see, the question asks you to explain your working. So we have to explain it in this way. We have to say that the centripetal force is equal to the frictions FF. So this one will give you 1 point. Okay, so we continue the working. We know that centripetal force is mr omega square. And we know that frictional force, as given here, it is 0.72 W, where W is the weight. So I will change it to 0.72 mg. W equal to mg. So I change it to mg straight away. And I cut the m on both sides then. So I know that the radius is 35 cm. In SI unit, it is 35 times 10 to the power of -2. Omega square is the unknown. We have to find omega in this case. So 0.72 on the right. The G is 9.81. So we can get omega by pressing calculator. And you will get 4.49 radian per second. So this is the angular velocity. So again, we have to understand that angular velocity is actually the angle the particle makes in 1 second. So in 1 second, the particles make 4.49 radian. So our question wants us to find the maximum number of revolutions of the plate per minute. So we need to know per minute. So 1 minute is 60 seconds. So we have to times 60 to our situation here. So by multiplying with 60, you get 1 minute equal to 4.49 times 60, which is equal to 269.4 radian. So in 1 minute, the angle makes it is 269.4 radians. And we want to know how many revolutions are there. So we know that one revolution is 2 pi. So we divide by 2 pi then to find out how many revolutions. So we get 42.9 revolutions per minute. So if you are wondering about this particular point, maximum number of revolution. So maximum especially. So the way that we understand the maximum revolution here is it has maximum number of revolutions. That means the plate is rotating at maximum angular velocity, and at that time it will have maximum frictional force. Imagine that it rotates at maximum angular velocity, and the small mass m is still on the plate. So at that situation, the mass will experience maximum frictional force. Okay, so which is equal to this value. Okay, so which means when the number of revolution is maximum, the frictional force will be maximum also. Okay, so that is how we relate the maximum number of revolution and the maximum frictional force here. When this is maximum, this will be maximum as well. Let us look at the next page then. The plate in B is covered when stationary with mud. Suggest and explain whether mud near the edge of the plate or near the center will first leave the plate as the angular speed of the plate is slowly increased. Okay, so you have to decide. This is your circular plate. So you have the center of circle here, and you have, let's say, one mud which is near to the center, another mud which is near to the edge. Okay, and the difference between these two muds is the first one you have a smaller radius, the second one you have a greater radius, and we know that centripetal force is mr omega square. So we have to say that since R1 is smaller than R2, I have to say that the centripetal force for the first mud have to be smaller than the centripetal force for the second mud. When we talk about centripetal force, we have to know that the first mud has a smaller centripetal force. That means in order to keep it in a circular path, we require less force to keep it in a circular track. But for the second mud, since it has a greater centripetal force, that means we need more force to keep it in a circular track. So at the same time, we need to know that two of these mud stay on the same circular plate. It has the same roughness, no matter it is near to the center of the circle or far away from the center of the circle. It has the same roughness and hence same frictional force. Frictional force provides the centripetal force. So because of the same roughness, they have the same frictional force, and hence they have the same centripetal force. But the second mud require greater centripetal force in order to stay in a circular track. As the plate move faster and faster, we can imagine that the centripetal force required by the second mud is greater and greater, and the frictional force can't provide such a great centripetal force, and hence the second mud will fly off first. So let us write down what we understand in words. It is just a 2 marks question. So first, what to write is, just go straight to the main point. Okay, we say that centripetal force increases as R increases. So mud at the edge flies off first as the frictional force that provides centripetal force may not enough to maintain the mass at the edge in circular path when angular speed increases. Okay, that's all for the first lesson today. Thank you.